All right, welcome to scalar projection. I want to talk a little bit about what scalar projection is first, and then I'm going to answer this question about a ball rolling down a hill. Sorry. So basically what we're trying to figure out is that this diagram here, right, we've got the ball, which is this circle here, and it's rolling down a hill that's inclined at 30 degrees. Now, gravity is pulling that ball down the hill. We're going to assume that there's no friction at the moment. We will later on. In questions, but for now, really, we don't need to worry. Just to simplify things and explain the idea, we're not going to worry about friction or air resistance or anything like that, but they're fairly easy to deal with anyway. Now, gravity, we can think of this like sort of vertical vector down here, right? And I'm going to call that G for gravity. That's working at 50 newtons, and obviously that 50 newtons, if you do physics, is dependent on the mass of that ball. So where we're just saying that gravity is pulling it down at a force of 50 newtons. So what will be the resultant force on the ball inclined at 30 degrees? So really what we're asking is, okay, well, what is the force that's pulling the ball down that way? What is the magnitude of that vector be due to gravity? So what we need to do is find out, well, how much of an effect is gravity actually having on this ball? And that's the idea of scalar projection, is that we're projecting the part of gravity that's actually acting in the direction that the ball is going to roll. Okay, so I'll say that again, where scalar projection is all about figuring out what scalar part of gravity is actually being projected onto the ball and it's forcing the ball down the hill. So before we have a look at that, I want to go through the idea of scalar projection from a formulaic point of view. So the scalar projection of V onto U, so we're projecting the part of V onto U down here, is equal to the magnitude of V times by cos theta, where theta is the angle between the two vectors, as it usually is. So what we do is we grab the vector that's being projected onto the other one and then times it by, or the magnitude of that vector, sorry, and then times it by cos theta, where theta is the angle between. Now that's great and formulas are good, but I find that scalar projection is a lot easier to work with if you know the theory behind it essentially and know what you're actually doing. And just using trig as it is, right angle trig as it is, because it's not always cos, sometimes it's sine. Well, we can turn it into cos if we want, and I'll demonstrate that up in the question above, why we can look at it being sine as well and not just cos. Okay. Lastly, just before we go back up and do that question, the vector projection, then we actually create a vector. It's just times by the unit vector u. Okay. But that doesn't come up that often, but still handy to know. Okay, so let's go back to this question. So what we're doing is we're projecting G onto B. So we can say that the projection of G onto B. Now, if we use the formula, right, that it's equal to the magnitude of G times by cos theta. But there's a problem with this question, right, because theta is representing the angle between the two vectors, but 30 is not the angle between the two vectors, right? The 60 degrees up here is going to be the angle between the two vectors. So we're going to use this formula, and then I'll show you how sine also works, and you might be able to think straight away how sine will work with this question. So we've got 50 times by cos of 60, and that gives us 25 newtons essentially. So out of the 50 newtons that gravity is pulling down, straight down on the ball, 25 of it, so half of it, is actually pulling it down. Okay. So obviously the smaller that angle between, the greater the force that's going to be. Okay. We can also use sine, right? If we didn't have the 60 degrees and things were a little bit different, we could have a look at this question and also think, okay, well, I can still work out, the magnitude of B, or that projection onto B. If we just do G times by sine of 30, right? Because sine of 30 and cos 60 give us the same thing, right? They're both a half. So we can actually use sine in this case and not have to worry about the angle between. So you've got a choice. You can just use right angle trig as it is and know your way around the theory. Or you can have a look at more of the formulaic approach, but always making that theta is the angle between the two vectors. Like I said, that's sometimes a little bit harder to get your head around, finding out when the angle between. And I definitely go with the idea of knowing what I'm actually doing properly and knowing the theory and using triggers as I see it. But it's completely up to you at the end of the day. Okay, so scalar projection. Sadler doesn't include too much of scalar projection in his text. So yes, awesome. So when we get down to 8b, which is scalar product and component form, you'll find that the question, or I don't want to show the solutions. The question, the past exam question actually gets you to use scalar projection there. So have a go at that, and work as well is really good. So have a go at those questions in the next lesson. But for this lesson, all you have to worry about is those textbook questions, and that's it. Okay, so have a go at scalar projection, get your head around it a little bit, and I'll see you in the next exercise.